welcome back. In this video, we're going to go over hash tables, which is an extension off of what we learned in the last video, which was the hashing function. And in this case, the hashing function is going to be used to determine where data should be stored within our tables here. So what exactly is a hash table? Well, you can look at it as a hash table as an associative array, basically meaning that each individual index here corresponds to some bit of data and information. We have keys that map to buckets, which have specific entries that are matched to the to whatever value they're placed at. So in this case, we take a look at some bits of information like John Smith. So we see that with our hashing function, it hashes to the value of 152 in our table, and we store that information. And then Sandra D also hashes to this value here. And as you guys can see, at the value 152, first we put in John Smith, then we put in Sandra D. So this particular implementation here is what we know as a separate chained hash table. Same thing applies to the right side over here. So another way to look at a hash table is its indices of buckets for data, which are computed by our hash function. So as we saw in the last slide here, we ran into an issue where John Smith and Sandra D both hashed to the same spot. And one way to resolve the collision is to basically append Sandra D to the very end of John Smith, meaning that we use kind of a chain here, and this is known as separate chaining. Another way to go over this is with open addressing, where what we can do is, okay, maybe Sandra D hashes to the same spot as John Smith, but what we might try to do is rehash Sandra D to the next available spot open from 152. This is known as linear probing. We could do quadratic probing, which might be a little bit better in this sense. So in some cases with all of these hash methods, once the table becomes too full, we actually need to resize the array and rehash everything. So we could also deal with collisions as a cache does, where we just overwrite the previous bit of data that was in the hash spot there. Another way to do this is two-way hashing, where we use two different hash functions and try to determine which one's the best. We also do that with universal hashing, where we try to find the optimal algorithm for hashing. And then we also have cuckoo hashing, which has multiple hash functions that are used in case one fails. So we move to the next. So I talked about the need to resize the table. So we have this thing called a load factor, which we use in order to determine as to whether or not it's good for us to resize and rehash. Typically, for open addressing, I tend to go with a 67% fill. In terms of separate chaining, a good number is probably 150% to 200%. So the load factor, how do we determine that? It's determined by the number of elements divided by the number of buckets. And we can multiply this by, say, 100% to give us the percentage. Otherwise, what we could do is we could view this 200% as 2, and we could view this 67% as 2/3. So, as I said before, when the load factor criterion here is breached, meaning that we go over it, what we need to do is basically double the size of our array, and then just kind of rehash everything. So let's talk about the average case running times of our hash tables. So search is very quick for the most part. On average, most of our buckets will only contain one bit of information. Now, separate chaining, with separate chaining, the hope is that we don't have to chain way too many elements per bucket. It's entirely possible that that could happen, and as you guys will see in the next slide, if that happens, the worst case search for the hash table will be n, because once we find the bucket, we need to manually traverse through each individual node in that list. So insertion, it's pretty simple and straightforward. With open addressing, you just put the element in that bucket that it's hashed to. For a linked list, constant time insertion if we're inserting to the very front of the list. If we have a reference to the back of the list and we want to append to the back, that's also constant time. So deletion from our hash table is going to be basically constant time as well. For open addressing, what we do is we find the element that we need to delete with our hash function, and all we really do is just mark it for deletion. We basically use this thing called lazy deletion, where we kind of say, oh, okay, that value no longer exists there, I'm going to set a flag here. So in this case, it works like a hash, where eventually if we have another element that hashes to that same spot, and we see the lazy deletion flag there, we can just take the lazy deletion flag and replace it with the new data that we want to insert. For separate chaining, it's just a simple linked list removal. Assuming that we're going to remove something from the very front, it's very quick and easy, and assuming that we don't have too many elements in our respective bucket. So for the worst case runtimes, we've kind of gone over the search here for our function here. So we've gone over the worst case runtime for separate chaining, where we have just one massive linked list in one bucket. For open addressing, what could end up happening is if we're doing linear probing or quadratic probing, what we might need to do is actually continually evaluate our function and manually search throughout the table to find this bit of information, because with collisions it's entirely possible that we could collide. We could have a collision for the value that we're searching for, and we need to probe through the array in order to find the actual value. So insertion in the worst case is a linear function. So what that means is in the worst case, our load factor is very terrible, and it's extremely high, and what we have to do is continually keep rehashing until we find an open bucket for open addressing. For insertion for a linked list, this is assuming that insertion is either done at the very end of the list or insertion is done somewhere in the midpoint of the list. And the worst case is all the hashes that we've had previously hashed to the same one bucket, so we just have a massive linked list. Deletion. The worst case is maybe what we have to do is resize our associative array after, or rehash, meaning that we have to continually we have to go search for the element in our array to delete, because we've used linear probing or quadratic probing. So in the worst case, we perform a search for the deleted item. The delete itself is fairly simple, where we just mark it as deleted, but we might have to search for it. So similar thing for the separate chaining. If we need to delete a specific node, what we might have or might find is that the hash function gives us direct access to the bucket it's in, but it's entirely possible that we have n nodes in that bucket, and the node that we want to get for deletion happens to be at the end of the list. That is the worst case runtime there. So here are a couple of references for that I used in order to make these slides. Of course, the Data Structures and Algorithm Analysis book in Java from Mark Allen Weiss. We also have a little bit from Wikipedia. And then Dr. Zahn's Hashtable lecture 8 from the University of Washington was also very helpful in constructing this. So I hope you guys found this somewhat useful. I'll be posting the code later for a hash table implemented as an open addressed hash table in the next upcoming days. So see you guys then.